Okay, good afternoon. Now after the first intensive session in the before lunch, we come now into the next session, the part 2, where I will give an overview about additional technologies and also about fabrication aspects. Firstly, I want to show a little bit to my background. So I studied solid state physics in Duisburg, and starting also with my diploma thesis, I was incorporated into the cleanroom. I made some developments directly in the field of accelerometers, directly inside the cleanroom in Duisburg. And now I'm here responsible for the whole 200 millimeter MEMS cleanroom. So from the background, I'm really hardcore technology guy who are working also in such cleanrooms over several years. And hopefully I can give you now a little bit more insights about other processes like MEMS areas. And additionally, what does it mean to fabricate something like that? In the first part, Wenke already showed an overview about the different topics inside microelectronics. You saw this picture this morning, where she was really more focused on this part 1, which calls memory, logic, and all parts which are consistent to that. It calls more Moore. Why more Moore? Because it's based on the scaling issue from Jordan Moore, from the Intel founder. And so it's mainly all dedicated to scaling. What we are now discussing are, they called it more than Moore devices. These are devices that have new functionalities which are not dedicated to normal semiconductor. So that's the main difference. And there are two really large areas. One is power and analog. Power I cannot, based on time limits, now cover today. The other part is opto and sensors, and especially MEMS, and there I will make a more deeper dive to it. And additionally, at the end, I will also show how such an climate impact or green impact will be calculated for a fabrication, and what does it mean? Is it really relevant for the future or not? Let's start with microsystem technology. What does it mean? Let's start with a definition. Microsystem technology involves really some special devices where we integrate also mechanical, electronical, optical, or other components onto a single substrate. That means often is a silicon wafer, then it's so-called monolithic integrated. It's a combination between electronics, optics, and mechanics. Sometimes when also the optics is inside, it calls MOEMS, micro-opto-electromechanical systems. So it's really in the same direction as MEMS, only with an optical part in it. And we have here at the Institute the main focus as a center for MOEMS, so for micro-opto-electromechanical systems. And additionally, what was mentioned by Wenke was then really the traditional or the next generation microelectronic devices. So from that side, what is the main application for that? There are possible functionalities which are very important. The first part, and there was the starting point, was microsensors. So sensors who can detect some parameters from outer side. It starts, I would say, with the first was really a pressure sensor to detect pressure from outer side. This started 1970 and something. and then it goes to other directions, for example, also microactuators. So you have small mechanical parts which will be in a certain way have a movement, and based on that they can generate some parameter changes in the surrounding. The first of that was, for example, inkjet heads. Inkjet heads for the printing industry, where to generate such bubbles was done by some piezo inkjets, and this was firstly done with MEMS-based processes. The application of MEMS or MOEMS, in that case sometimes the O is not inside, is tremendously in all directions. It goes from automotive over electronic, medical, defense, and also in communication. And it's a very important add-on in the microelectronic industry. When you think about automotive, for example, you can think at the first stage, for example, for ultrasonic sensors, the distance sensors which you have in the car. But also specialized now in the new autonomous car system, so to drive it driverless, there are a lot of opportunities. And I was, for example, involved at my beginning was the accelerometer and the gyroscope, which was very important, and this was a breakthrough for that. I do not know, no, nobody for here will remain this or remember this. This is done. There was an R-class car from Mercedes who had some problems because they flipped to the side when you go too straight forward into a curve. And for that, Bosch developed an accelerometer and a gyroscope that the electronic system inside could prevent this, so that you cannot go too straightforward into a curve. This was really 1994, 1995, something like that. And this was really the breakthrough about such electronic inside of cars. Of course, also a very tremendous system, or where you will have it also in your surrounding, is in the medical business. There are a lot of devices you will use, but you do not know it. For example, when you measure the blood pressure, there's normally a MEMS-based sensor inside. Or when you really make some analysis of some blood parts inside, will be also normally done with some special parts from the MEMS business. And last but not least, communication. That's, I think, consumer and communication. There's the biggest one. When you look at your smartphone, you see here all of MEMS-based sensors inside, which you do not think about in the normal use. It starts with the camera. Of course, there's no mechanical inside, but nevertheless, without a camera, without MEMS, the camera would not exist. We have very important such proximity sensors, magnetometers, accelerometers to count your steps each day. This is done by a gyroscope and accelerometers. And the most important one are microphones. Microphones, at the beginning, you had some issues because these are all based only on some fine mechanical tuning. And then the first silicon-based microphone come on the desk, and today you have several microphones inside of your smartphone, not one, because everybody uses it in a different way. I saw somebody who you speak at the bottom, some on the top, some on the rear side, some on the front side, I do not know. And for all these issues, you have a microphone there inside. And this is very important for, of course, the communication, because, and this is the same as you have it for microelectronics, the cost of such microphone comes down tremendously. So at the beginning it was really by several euros or several dollars, and now you are in a cent region or 10-cent region for a microphone. So from that side, it doesn't care about such a cost. And the reason, based on these devices mainly, the amount of MEMS devices, and this not many people know or recognize, is tremendously growing. You see here over the time, starting 2001, what the historical shipments as a summation what done into the market. And we are actually about, when the numbers are here right, in the field of 40 billion devices. So a lot of devices which are in the market. And one additional aspect is very important. When we discuss always about microelectronics, we only discuss mainly about Asia. In the MEMS business, we have two of the largest MEMS fabrication companies here still in Europe. One is Bosch, it's number one. One is ST Mikroelektronik, who is sometimes number two, number three. So from that side, where the main industry for MEMS devices is located still here in Europe. And this is, of course, for us also important, because local industry in Europe we also want to support. And this gives you an indication where it go into the future. And there's, of course, a lot of new ideas where you will use MEMS devices in the future. So from that side, we have to subdivide, when we discuss about microsystem technologies, three classes. One it calls surface micromachining. This means that on a wafer on top, additional layers will be deposited and structured, and the functionality is on the wafer surface. That's one possibility. The second one is bulk micromachining. This means that you structure the wafer itself. I will show some of these pictures. Based on that, you use the whole wafer, sometimes a part of a wafer, but the whole wafer as a sensing or mechanical element. And third, this is a combination about one surface micromachining and normally then CMOS. So you have below the MEMS devices also a completely readout circuitry. And this is the most complex one, because you have to combine two process types together to bring a new functionality inside. And this is often also called monolithic integration. And I want to show you some of the most important ones. For example, here, this is an accelerometer from Bosch, where we have on the left side the MEMS element and then the ASIC for the readout. And how it works, normally you have a seismic mass, which is supported by some very thin silicon parts. And then based on the acceleration, it moves in a certain way. And this movement will be detected by capacitance fingers. And the capacitance changes then, and this will be detected by the ASIC. So that's a very, very simple in question mark, but it's very important to have it in a good accuracy fabricated. And this was the first implication for that was for airbags, so that you in a certain way detect when you have a crash. But today you do a lot of things more with these sensors, so also pre-detections and also steering implications to the system itself. And it will be used not only in the car, it's used in aircraft, it will be used in space where you want. The other one, which was the oldest, I said, was mainly pressure sensors. And here a pressure sensor which I already developed, so it's part of my background history, so that's the reason why I put this. This was a surface micro-machined pressure sensor on a silicon substrate and also on a CMOS later on. And you see it here, you have a cavity from the side. I want to show it to you. There's a small, no, one moment. You see here the small circles that are small cavities. And each cavity is a capacitor, and when the polysilicon membrane will be deflected by the outdoor pressure, then you can measure the capacitance of these circular rings, and based on that you can detect directly the outside pressure, because the inner part, what you see below the polysilicon, is evacuated and closed at very low pressure. So and the force which go to the membrane is the force between the outside and inside pressure. And based on that, it's very easy to implement this. We had it, for example, for the heart catheter, where you can put it into the blood chain, and then you can measure directly inside the heart your pressure. Or you can use it, for example, for tire pressure measurement. So when you drive a new car, normally such pressure measurement is already installed inside the valve of the tires. And this we developed 1996, so it's a long time ago, and now it's standard. So from that side, it's really an interesting fact how it grows over the years. So based on that, these are only two examples. I also want to show you, because we are here a little bit Mikroelektronik and Microsystem Development Center, I want to show you additional processes based on some of our daily work, I would say, or what we do. And I shown this slide already in the morning. This is a little bit our portfolio where we are working on, and I want to show to you some of such devices and what does it mean regarding how we fabricate this. Interesting fact, because the discussion was this morning, why there are so many fabless companies in the market. It's mainly because microelectronics you can easily standardize. So from that side you have some technology nodes, and you can subdivide it, the fabrication and the function. So the function, you can use some elements which are already standardized inside such processes, and based on that you get new functionalities by combining such different elements. For example, transistors, resistor, memory, as you want. When we are discussing about MEMS, this is still an ongoing thing. A lot of people try to standardize this, and this is very difficult because you have no standard elements, or very difficult to generate standard elements. So from that side, often each device has an own process type. So we have not this different scaling, what we get from microelectronics. Nevertheless, when I think about when I started with some pressure sensors, they were very large, and today you can have it on 1 square millimeter, a complete pressure sensor. At the starting point, it was 10 times or more larger. So from that side, we also use there some scaling, but specialized on some sensors. So let's start. One start is an actuator and a sensor. It calls a capacitive micro-machined ultrasonic transducer, or in short name CMUT. It's an ultrasound sensor or actuator. The idea is to detect and to measure also distances by ultrasound. And for that, it will use a special technique which is very near to the pressure sensor you saw before. Here we have the opportunity to really highly miniaturize these detection. When you discuss about sonography, so when you go to the doctor and they have this ultrasonic or ultrasound system detection, there are still some handmade electrodes inside. Could be a column about 1,000 or more devices. And this is very expensive when you see such a head. With MEMS, there is now from Butterfly Technology one fully integrated MEMS electrode system on the market, which you can directly connect to your iPhone, for example. And so you can make, in principle, your ultrasound measurement at home. The doctors are not so very favored about that because when you saw already such pictures, it's very difficult to see the white things. And for that, they said, okay, I do not want to do this at home. Nevertheless, it's an application which could be interesting for future to reduce also the cost of such systems. And we are working on that. And how it works. You saw here the pressure sensor, and it's nearly the same. You have a cavity, and the cavity get an additional. One moment. There is now a problem with our. This is normal every time. In the time period, it's switched off. Now it's on. In a principal way, you have also here a cavity, and the cavity will be pre-deflected by a normal voltage. Then you have it a little bit lower and have a higher capacity, a higher sensitivity. And then you put on that, for example, when you want to transmit some sound, you put some AC voltage to that. And based on that, the membrane swings over a certain distance. And based on that, it could then send sound to outer side when you are in the kilohertz or more range. On the other side, you can also receive. Receive means in that case that you have it also deflected and you see the dynamic changes of the deflection, also by capacitance, as you saw it with the pressure sensor. And based on that, you get then also nearly a microphone for ultrasonic. And how it's done, here you see a very simple description of the fabrication technology. On one side, we do it as a surface micromachining with some membrane will be put on top of a so-called sacrificial oxide or layer. And this sacrificial layer will be then etched away by a wet solution. And then we close the channels by a certain pressure and put also an additional electrode on top. And based on that, you have your cavity. Very simple. You can also do it by bulk micromachining. You can use a bottom wafer and a top wafer. And then you bond each wafer to each other. So you have one wafer on top of each other. And then you have also there the cavity, which you can then also detect. For doing that, you have to use very thin wafer, or you have to thin the wafer. And this generates then also the cavities. And these cavities could be then, when we are discussing about lateral distances, we are discussing about 100 or 200 micrometer up to millimeter, something in this range. What we also can do, and that's I want to show because it's very, very unique here. We discussed, okay, can we do also not ultrasound, we can also do here really normal sound. And this we done with a special principle. I do not want to go into the detail, but you see it here in a principal way, that we have some wafers, we make very deep structures into it, very thin but deep structures, and based on that we get then some columns or some special clamps which are then moved to each other, and you have something like an air pump, you can say. You know? You pump really from the outer side to the downside really some air. It's like really an air pump. And based on that, when you do this with frequencies in the sound business, then you can also generate sound as a really normal loudspeaker. And this is very unique, and you see here as an example how you can then use it for really to make a loudspeaker. And you see here the movement of the whole system. You see it's much more complicated than I said it now. And then you put on top and on bottom a wafer. One moment, it will come. So now it comes from the top and the bottom as an additional wafer, and then you put it into your earphone or air plug, and then based on that you can have an in-ear loudspeaker. And it will be funny in that case that it's up to now each loudspeaker you have in your smartphone or in your phone is in-ear earbud is still mechanical fine-tuning by manual mounting. And this is a first all-silicon MEMS speaker. And this was a really invention we made here based on this principle. There are other on the market who are working on that still. And here I also want to say this is very a success from Fraunhofer IPMS, because we made a spin-off out of this principle, and this spin-off was sold about 1.5 years to Bosch, and Bosch want to produce then such loudspeakers in mass production in the next years. So for us is the next big thing in the smartphone business, that you also now get not only the microphone based on silicon, you can also make the loudspeaker based on silicon. And really the sound quality is tremendously good. So it's really a very, very good loudspeaker based on some optimization we put there inside. So when you see in 2 or 3 years then some earbuds or how it calls on the market where all silicon was on top, then you know it comes from us. So that will be, of course, a very interesting fact, because then, of course, the costs go down and additionally the quality will be still high. One other issue is then now in the actuator field. We are working very deep in MEMS scanners. What does it mean? MEMS scanners are 1 or 2 dimensional moved mirrors, single mirrors, which can be used to deflect light in a very simple way with the movement of the mirror. And what can we do with that? And the main application which is actually on the market or is in discussion is automotive LiDAR. This means that you have not radar in it, you use a light scanning of your surrounding, and based on that you know where the cars are located around you. And this is actually done only by a big mechanical system. And with such MEMS-based system, it can be much, much smaller. That's one part. On the other side, it could be also much more robust because the amount of the weight of the elements are much, much lower than we have it when the traditional mounting is there. And to give you an indication, there's on YouTube also with our partner a test where they detect with such a system and a laser cars in 1 kilometer distance over the whole system. That was really tremendous success because the mirror diameter is only 1.5 or 2 millimeter. And then you get it from 1 kilometer back. So based on that, this was, we never thought that it's possible, but it was possible. And how it looks like when we want to produce it, you have this mirror, and the mirror is in a plate. You see it two-dimensional on the lower left. And then you move the complete plate based on some resonant activation based on interdigital structures. You see it on the white above. There you have some plate deflection based on capacitance based on the voltage. And this voltage generates in a resonant way deflection. And this can be used in 1 dimension or in 2 dimension, of course. And based on that, you can then deflect your light in 1 or 2 dimensions. This is a very interesting effect which will be used in different applications. We have also scanners who scan then some lighting area, some areas with such scanners, and also one of the microscope, for example, for size, is also done by such scanners, so light blade microscope, and from that side there's a lot of opportunities what you can do with that. When you not do one mirror, when you want to do it more than one, then we are discussing about micromirror arrays. The micromirror arrays, you have then 1 or 2 dimension areas, arrays of small micromirrors who deflect then the light or diffract the light in a certain direction. What is the main application? You are sitting in front of it because this projector you have here has a DLP inside, the digital light projection system from Texas Instruments. And this deflects the light to generate then this picture in a very simple way. So they have a lot of individual moved mirrors, and based on that you can generate such a picture. It will be also used then in normal cinema projectors. When you go in a cinema, you normally have such such lighting modulator. What we do from our side is a different application because this part is high volume for Texas Instruments. We are working more accurate, I would say it. You have here such a micromirror, and this micromirror can deflect in 1 direction and is a pitch of 16 micrometer, so very small. What you see on the left side, this picture is in that case really 1 million pixel. So it's 512 by 2048 pixels. And this can be moved in a 2 kilohertz frame rate. And this will be done by some electrodes, you see on the right top one, by really movement or by applying some voltages to these electrodes. And based on that, you get some deflection in 1 or the second direction. Very simple. Now it's simple. But we have to do it very, very accurate. This means because we use it for diffraction Fourier optics, and this means we have to have a position of this tilting which have to be in the nanometer range. And this reliable over several long periods. What you use for that and what is the application you see here. This was really for exposure of masks for the semiconductor industry. This was one of our largest projects, and this is a mask writer where you get on the fly some writing of some patterns into the mask area. And we use for that, as I said, Fourier optics. So it's not a normal deflection. We're using a local diffraction pattern, and this will be then used to exposure it downwards to the mask. What does it mean? Based on that, we can get, you saw 17 micrometer is the distance between the pixels, but we can, by a factor of the projection, we can generate then lines of 140 nanometer downwards on the mass. And this was very important. And additionally, by having some small changes in the diffraction pattern, we can shift the one part of the line and spaces in the nanometer range. So very, very high accuracy. And to make such a system, it's a tremendously effort. To give you an indication, below that is a CMOS. So what you heard in the morning is below. And then we have additionally put on top such micromirrors. And we will see later on how it will be produced when you go downwards. But we have then today up to 800 process steps additionally, which we need to generate such micromirrors. And so you can imagine such a system is not very cheap. That's the reason why we do not do it for such projection. But we are looking in the future, and we can scale it down still, and we are in a scaling issue to have it as small. We have now 70 micrometer, smaller pixels to generate then later on holographic pictures, to make digital holographic parts based on this projection. Because we are much below the diffraction limit, so from that side we can really change also the phase of all of the lasers we put on top. So from that side, this is the future. So the first structures are out of our clean room. So we want to generate then digital-wise some holographic parts, which I think will be an interesting fact in the future. We already dream over several years about that, and it could be that it will come in the next decade, that we also can really then have free-form holograms. This will be, of course, an interesting fact. Science fiction movies already have it, but it's still a long way to go. And to fabricate this is really, really hard stuff. It's not only by scaling, but to get a surface which is so accurate and so planar, as you see it here in this application, is a really big issue. So, yeah, last but not least, I want to say something about OLED on silicon, which is not really MEMS, but I will put it inside this part. The idea there, you have a CMOS backplane, and on top you make organic light emitting diodes. Do not know if you know what this means. Organic light emitting diodes are diodes which are made on carbon-based materials. It's like plastic, I would say it from that side, a very simple way. And these systems will generate then a diode, a light emitting diode, which can then easily be structured on top of a CMOS. And based on that, you get then a very small TV screen, I would say it from that side, or a screen, which you then can use for projection. Not for the projection here, what you see here, this is for DLP, then for directly head-mounted displays. For really such, or Google Glasses, or how they want to go in that direction. For doing that, you need as firstly the CMOS, and then you have to put these different layers of these materials. There are different materials on top in the nanometer range, and then you can generate such light. You will see it later on when you go downstairs. There are some of these displays presented. What is here also a very interesting fact, you get very high brightness levels based on that. And it's very, very low power. We are discussing here in the range of milliwatts for doing it, really to present it to some customers. And when you want to do this, we are here have the world record of the smallest or the high densities micro display. It's a 0.18 inch display with 10,000 dpi, dots per inch. To give you an indication, your normal display has about, in the field of 200, 500 dots per inch, something like that. We are in 10,000 dots per inch. And this was done together with Global Foundries on a 28 nanometer range technology node. And then we put on top these OLED with a very high resolution, 1440 by 1080 pixels. And you will see it later on. Up to now, it's still a monochrome, but nevertheless, it could be also done with in a certain range with also color. Then you put color filters on top, and based on that, you get a full display. And this gives you, of course, an indication that we have some interesting future markets, because this head-mounted or glasses, this intelligent glasses is still a topic for the future. The first really, I would say, usable glasses comes on the market by Ray-Ban, for example, but they are still only by acoustic feedback. What we also want to have some directly augmented reality by project some data into such a display, so that when you go to the street, that you can directly receive some information during normal looking through the outer side. Okay, we have still here the next one. One moment. Zap. Now we have it back. So from that side, this gives you a certain overview what we are doing here with MEMS, and you see the tremendous wide possibilities to use it. Now is the question mark, how can you do this? And what does it mean then later on for sustainable electronics? What does it mean? That are the next two question marks. And before we do this, my conclusion would be that we may now make a 10 minutes, 15 minutes break, because this is now a good opportunity, so that we are here at 2:30, and we start then how it will be fabricated and what is the green impact to that. Okay, then I would say starting with a break and come back then in 15 minutes, okay? It's a long day with a lot of lectures. Are you still fit? Are you still? Looks. So it's only now 45 minutes left, and then you can go and can see also something. Then you have survived the lecture business, but then you have hopefully also some ground level that you can see where we want to go. So from that side, it's of course for us also a question mark at which level we want to start. So when you have some questions, please interrupt me, no issue. For example, interrupt me that you hear me in a better way. No, please ask it directly or then later on the tour, because it was for us, of course, also an interesting fact where we want to start. We do not want to bore you, but we want to also give you some fundamental information that you know what microelectronic and now also MEMS technology means. Now we come to the microelectronic and MEMS fabrication. And there directly a question mark, who were already in a clean room? Great. So from that side, at the beginning there was a lot of discussion about what is a clean room and something. There, of course, Wenke gives some background. I do not want to go into much detail about that. It's more how it deals then with sustainable calculation. Okay, when you were already in a clean room, then you know about the fabrication process in principle. In principle, we have normally a process workflow. This is subdivided in different process steps, how it calls. And this process step will be done on certain process machines. And in a principle way, the cycle of fabrication is always the same. Normally you make a layer, forming a layer by oxidation, CVD, PVD, electroplating or so on. And then you make a lithography. You make some subdivisions. And then normally you make the structure. And then you restart the process cycle. That are the main parts of a fabrication. And then you have a lot of process steps, normally for each of such a cycle, about 20 or 40 steps. And when you do this layer by layer on top, then you get at the end microelektronik, microsystem as you want. How much count we are discussing about, I mentioned it before the break, that we have up to 800 or 1000 steps. And this is also the case of microelektronik itself. So when we do our SLM, we get it from external already these CMOS, and then we put on top really these MEMS layers, 800 steps, and the CMOS itself had also, I think, about 600 steps. So this is a really hard, complicated process. And somebody said already that semiconductor technology is the most complicated process in the world. And the reason is also that nobody in whole world can do it by their own. The whole industry is completely connected to each other because no country can do all of the machinery, all of the process steps, all of the chemical by their own. We have to be connected, and then we'll show this already, or we'll show this. And to do this, now we go to the next step. What types of process steps are there important. And you see here now a big table with a lot of steps, and there are much more than that. This is only a small, I would say, overview. It started with some cleaning procedures, over surface treatments, about photolithography. I will go more into detail. Then we have also some parts with ion implantation to put some additional carriers into the silicon. Etching is a very important part, to etch away such layers in a certain way. Then the deposition parts. You heard in the morning about ALD, atomic layer deposition. The normal one is CVD, or thermal oxidation. I will also discuss about that. And then we have some additional thermal treatments, or we have also CMP, chemical mechanical polishing, which you will hear also in the next days something about this. Last but not least, when it's at the end, we also have to test everything. And each form of these boxes you see here needs a special machinery and a special process to be optimized. And so you can think about how complicated is this to make it as accurate as possible. And this is the reason why it was really a funny thing during the COVID area. There was, as you heard, some shortage of chip production here, especially for the automotive industry. And we had a very funny, I would say, discussion about, could we produce in our clean room some circuitries for the automotive industry to overcome the shortage? And we said, no, that's not possible, because to only implement such a process completely inside our clean room, also when we have all machinery we need, takes several years. So from that side, it doesn't, you cannot do, today I make it microelektronik, tomorrow I make microsystem. That's not possible. It takes a lot of years to optimize these processes. And you do not see it as a consumer, but the amount of hours of optimization in such processes which go into it is really huge. But principle, we have some very simple process types. But before that, I want to say something which have to be done in the morning in a certain way. We do it normally of different size of wafers. Wafer is the ground plate, which is normally monocrystalline silicon with different sizes. We here started with 4-inch in the 1990s. And now we have 200 millimeter and 300 millimeter. And this was also the historical way how it grows. And here nearby in Freiberg, there is also Wacker, for example, who has a very long history in producing such wafers. It's this an own mysteric high precision fabrication. And because to get such wafers monocrystalline with good quality out of such a fabrication is by their own a really hard stuff process step. And for that, why it's always larger? Well, it goes to 200 to 300 millimeter, and there was also a discussion point to 450 millimeter, which is still only something for the future. It's very simple, because the cost of the machinery goes not in the same direction, or was not so increased in the same direction or the same amount as the area of the wafer grows. So when you come from 200 millimeter to 300 millimeter, the machinery costs then, for example, 30 to 50% more, but that's lower than the amount of area you gain. And so the cost goes down. That's very simple. And also when now the highest, also the most advanced machineries cost about 200 to 300 million, we will see later on. Still the scaling was till 300 millimeter in such a way. Of course you, yeah?
We see that the diameter getting bigger means more surface area.
Yeah.
Why should the thickness be bigger?
Because you have to handle it. When you have it too small, you get some bending of the substrates, and this gives some some problems regarding lithography or exposure or to use this. So that's the reason. So it's very simple mechanical issues. Yeah. Okay, so actually for microsystem technologies, the standard is 200 millimeter, and for microelectronics is 300 millimeter, and we have both in our institute. Now let's go to some, I would say, principal process steps to give you an indication, and this gives you then also an indication what we can do to make it more sustainable. The most successful process step for semiconductor based on silicon is the thermal oxidation. Why? It's so simple. Because you make it only as a hot tube, and to the hot tube you put some of the ingredients you need, and then the silicon oxidize to silicon silicon oxide. And based on that, you have a very, very good isolator. This was really over several decades the really success story from silicon, because it's so easy. You put it inside of such a tube, makes the oxidation, you have a very good oxide layer, which is used inside of a transistor as a oxide separation for the field effect transistor. So from that side, this was over several years the best one. Today we have other materials also, so it's much more complicated, but to give you as a background, this was really the starting point. But you see directly what can we do to make such a process step more sustainable. And we done some optimization on our side also. The main part is, of course, how you handle the temperature in such a furnace system. When you open it and just go outside, then the normal furnace will go down on a certain standby temperature. And the question mark, which is the standby temperature? Normally you discuss about 950, 1000, 1500, 1050 degree. And then you can go down to 800 degree, or you can go down to 700 degree. Of course, this is a completely difference in the efficiency and can generate some best opportunity to reduce the power consumption of the whole system. On the other side, you can also reduce the tube dimensions in a certain way, that it's not too long or not too short. All this, it could be done, and this reduce, of course, then the possibilities of the power consumption of the whole system. Second one I want to show, so that's so simple, I can do it with one slide. The second one is lithography, which is much more important, I would say, for the next generations. Normally you do it in such a way, you have your wafer, then you coat it with photoresist, then you make a pre-bake, then you make an exposure, and then you reduce or you put away this exposed resist. And then you make a development to make it stable. And based on that, you have a masking of some areas, open areas. There are several possibilities how you can do this. The simplest way is, of course, to make it by so-called contact printing, so one-to-one imaging. So from that side, very simple. You can do it by a simple mask, which is in a certain way a one-to-one mask, which is directly in contact with the wafer. This was at the beginning, I would say. Nobody does this still. And the next one is proximity printing. It's also one-to-one, but you have a distance between the mask and the wafer. Okay, that's simple, but still the mask features have to be in the same dimension as the features which you want to have on the wafer. What everybody do today is projection printing. So that is typical 5-to-1 or 6-to-1, where you have a projection then on the wafer. And normally, to have not too much mass sizes, then you have normally only a part of the wafer will be exposed. Normally, 20 to 20, 30 by 30 millimeter. And then you go to the next chip and makes an additional exposure. That's the reason why this system calls stepper or step scan. Then it's a scan additional inside. So it steps from one chip to another. And so you fill then your wafer. And this was a long transition how it would be optimized. And this is really one of the most complicated process steps. That's the reason why I mentioned this. And you will see it also when you go around our clean room, that this area is very important, the most cleanest one, and additionally the most expensive one. So the machinery is the most expensive machinery we have then in our line. Because firstly, you need to optimize the structures to get on the exposed resist the right structures. That sounds very easy, but when you go below your wavelength, when you exposed it, then you get not a direct normal structure transfer. You need some special assist structure to optimize your pattern on your wafer. This calls then here proximity and masked additional structures generation. And additionally, of course, these masks have to be generated by their own in a good quality. And this is an own fabrication step, which is here also done below in our clean room by the company Photronics, for example, who produce such masks by e-beam writing. And then the mask will be etched because it's based on chromium. So you have chromium on glass. And this is then the mask which will be fabricated. Then you have the lithography tool. And after that, you also have to check it in a certain way to have to measure the so-called critical dimension. You have to measure, is the exposure done in the right way? And there is, this will be done by an electron microscope to measure it really in the nanometer field. So we are discussing here really about the highest accuracies you can think about. And to give you there an indication, you see it here over time. We started a little bit with 365 nanometer exposure wavelengths, which calls I-line. And then there was also 248 nanometer. And as lower the wavelength, as more accurate, as smaller all of the exposed wavelength structures could be. And you see it here, the feature size goes down, down, down. So 248 nanometer, this is also, you will see it on the tour, 365 we have, 248 nanometer we have. Then the next one was 193 nanometer over several years, you saw it. No? And then the really tremendous step comes EUV, 13.5 nanometer. To give you an indication, here we are discussing 365 is still, I would say, blue line. 248 and 193 is UV. And EUV is like X-ray exposure. And to do this important step, there was a lot of discussion point in between. Do we have at 157 nanometer wavelength a still additional exposure point? But this was really overcome directly by the EUV tool. And this EUV tool, 13.5 nanometer, looks very easy, but this is the most advanced machinery you can think about. And only up to now, one company can do this ASML in the Netherlands. From that side, near Eindhoven. And these are the most, I do not know if you heard about the semiconductor war a little bit. This is based on this machinery. Because this machinery took over a decade, more than a decade development, and are the most expensive one, and up to now, only ASML can produce this. Here you see, for example, our track for 248 nanometer. Such a track costs in the field of 10 to 20 million. So that's really hard stuff. It comes from Nikon from our side. But when you want to go really to EUV, you come to something like that. This is a real picture. To give you a little bit the size of the machinery. Such a machinery costs between 300 to 400 million euro. And now you can think about who can use something like that. And somebody calls him the most complex machine in the world because it's so complicated. And over several years, a lot of people tried to copy it. Up to now, it was not possible. That in the future, I do not know. But there are so many put inside, including the source. The source was really problem. The really exposure was a problem. The resist to what you use there is a problem. And so this is the main success between, for example, the most advanced process types you heard in the morning and to do it not. So from that side, of course, you need also a production volume for such a machine. In other cases, it will be really a loss when you cannot fulfill or can fill it with some production levels. So that is really the high top part. And this is the reason why ASML is also the company in Europe with the highest market capitalization here in Europe. Very interesting. I was one time at ASML. That's really impressive. Next part is dry etching. Dry etching is one of the most used structuring technique now in modern processes. And there are several possibilities how you can do this. In a principal way, you can make an ion in a plasma, and then you accelerate it to a substrate, and based on the physical application, you get some structuring. That's the simplest way. It calls physical etching. What you can do, you can make it in a different way. You make it with low acceleration, and then you get a reactive particle inside, and you make some chemical etching at the surface. Of course, you get then a reaction product, and this reaction product will be then, I think on Thursday, very important, where we discuss about abatement. So what you do out of the machinery with such gases. What you can do is a combination of it. You have a reaction particle, an ion particle, both. So you have so-called reactive ion etching. It's a combination between chemical etching and physical etching. And this is, in a principal way, the most used type. And you can imagine that the selectivity, this means you have a forward etching and a sidewall etching, is different when you go that or that based on chemical or physical etching. More physical etching goes straight through it. More chemical etching, you have some anisotropy, which is smaller. This you can see here. And of course also the selectivity. So when you have different layers of different materials, how selective is the etching against these different materials? Of course, when you make chemical etching, you can make very easily between oxide and nitrides. There could be different possibilities to optimize, and you can then get, for example, selectivity of 100 to 1 or so. But when you make it only by physical processing, you can imagine that it's something like throwing away everything of your layers. Then, of course, you have no selectivity. Then it's like scrubbing the surface. So in this combination, we are ongoing. And to doing that, you will see also at our line, often we use this combination reactive ion etching. And this reactive ion etching is in a chamber with some etching gas, with some plasma area, which then have some forward voltage that you have a bombardment on your wafer. And have a physical and chemical etching. And you see it here, the etching gas, of course, go inside, but go also outside. And this is, of course, an important aspect for the GVP or the green impact to outer side. You will hear it, for example, when we have an etching gas inside SF6, for example, a very prominent one. This SF6, when it goes to outside, to the surrounding, has an impact to climate more than 20,000 times higher than CO2. So when we put this only by ourselves to outer side, then it's a really tremendous impact to our carbon footprint of your process. So, for example, also on our side, we have some programs running to overcome these gases or to crack them. That's called abatement, to crack them and to give it outer side to have a lower impact to the climate. So, and in the former times, to be honest, nobody cares about that. So that was really now in the near past that a lot of people said, okay, what we do with FF6, what we can do there. Not only we, because also SF6 will be used, for example, for sound absorbing glasses, window glasses. And so when you open it then it go outside and will directly pollute it into the environment. Okay, this is, I think, now reduced in a certain way, but on the other side, which is still used, is in transformators. Transforming systems, for example, in wind turbines, there's still SF6 inside, and to replace such turbines without makes the exposure of SF6 to outer side is an important aspect. Okay, when you do it right, it looks something like that. I said we are dealing with microelectromechanical system, and here you see really micromechanical systems. This is, for example, some structures which can be used really as a mechanical parts. But you see the anisotropic, it's really hard steps inside the silicon, and this is, of course, an important aspect when you use and want to structure such materials. Okay, to do this, I mentioned this morning already, we have, in that case, 3 cleanrooms, one for MEMS, MOEMS, one for microdisplays, and one for micro and nanoelectronics. And only you will then go around. For our 200 millimeter cleanroom, you see here how such systems are clustered. So we have then here the whole cleanroom, and we have the lithography area, you have a PVD, CVD, etching area, you have a CMP area, a thermal area, and also some other deposition. And last but not least, very, very important, measurement area. We often need, of course, to measure all the structures, how it looks like, and how we can go on there with the next steps. So particle will be measured on top. We looking at every dimension you can think about. We have an atomic force microscope inside to really detect really small steps or small particles. Something you need all inside, and additionally you have the wafer testing, last but not least, which is also located there. And when you go around, there is about in the near of 200 million euro machinery installed, only in this small research fab. And to organize this with these different machinery, this is an important optimization point to reduce also the amount of energy we need in different areas. Why? I will come now through it. Because now we come to the issue, we know how we fabricate, but what is really the impact of such a semiconductor fabrication? And this I will give you a small outlook, because tomorrow you will get some skills regarding LCA, so life cycle analysis of whole systems. Nevertheless, I want to give you a certain, do we have an impact? What is the impact of semiconductor in relation to other ones? And to do this, firstly, we have to analyze what we want to analyze. We have, of course, chip design, which has also an impact. Then we have front-end manufacturing. This is what we discuss. And then we have the mounting technology, which calls back-end manufacturing, which is the third one. And all these parts has some critical inputs, like equipment, chemical, wafers, materials, as you want. We are here focused now on what I wanted to show to you through the front end, because back end is an additional part. But also there, how you calculate now the impact. And there you can take with you, there are 3 possibilities. It calls scope 1, scope 2, scope 3. Scope 1 is that we are looking at the direct emissions based on our own equipment.
Just one question to front end and back end, because as I studied, I did not know what front end and back end is. And then the rest of the conversation I was lost. So maybe you can explain shortly what front-end manufacturing and back-end means.
Okay. In the simplest way, I would say it from that side. Front-end manufacturing is everything which is done on the wafer with the wafer. And back-end is everything where you structure it when you saw the wafers into certain chips and mount this into some carriers or mount this on a surface in a certain way. So that's the main transition point. So normally you have a front-end fabrication which is all dealing with wafer, and then you have the back-end manufacturing which is based on chips. They are in between something, but I do not want to disturb based on this heterogeneous integration. This is in between of that. Nevertheless, this is you can think about. What we are discussing here is a front-end fabrication clean room, and also at the CNT side. Also what you see with Global Foundries is front-end. The back end is normally, the traditional one, is normally located somewhere else. So from that side, this is often a question mark, how much back end we have to do in the front end and back, vice versa. Good. And to doing that, as scope 1, as I said, are the direct emissions sourced, controlled by the company itself. This is everything, the use of material, the use of energy. That's very important. And then we have scope 2. Scope 2 has also indirect emissions. For example, to get such a clean room, to organize such a clean room. And especially also power consumption, so energy consumption, the power we get from external. And then there is also scope 3. That's the most difficult one, because there you have then also bring indirect emission based on the producing of the materials from outer side. And you will see now some ideas about scope 1, scope 2. Scope 3, I have also one foil to it, but it's really complicated to do this in a whole way. And you will see the numbers very hard over the several scopes. So, and there's also two parts of possible approaches to regarding such calculation. I directly say not life cycle analysis, because there should be also something more inside, so the GWP, so the global warming potential calculation. One part is top-down. Top-down means I calculate all the completely emissions for the completely clean room, and then I make it very easy and say, okay, I have several count of wafers. We are about 15 to 20,000 wafers in our per year. For example, X-Fab beside us has more than in the field of 150,000 wafers a year. Global Foundries are still on the way to 1 million wafers a year. And then I easily count everything, every wafer and the chip area which is on it. And then you get, by dividing it, very simple, kilogram CO2 equivalent per square centimeter die area. Die means the chip which is cutted then from the wafer. That is without housing, with everything else, only the cutting, this chip, small silicon tile. And this is one possibility. On the other side, when you want to optimize some process steps, this top-down version is not very good. Then we are looking about bottom-up. Then we are calculating everything for each process step and combine it with the indirect emissions. And then we make it only to inside a lot. A lot is a combination of several wafers. And then we can also can calculate the area, and based on that we get then kilogram CO2 equivalent per square centimeter. Yeah?
You said before, like you have like 800 to 1200 production steps. I've
Yeah.
already calculated some LCAs.
Yeah.
They were just like maybe 10 processes or steps.
Yeah.
And so there still might be some production steps that are pretty similar.
Yeah.
I think. So it's maybe not 800 to 1000 or so,
No.
maybe a little less, but it's
Yeah.
still a very high complexity.
Yes.
And how do you calculate this with the bottom-up approach?
That's the reason why it's still an ongoing thing that everybody will calculate this bottom up, because it's a tremendous amount of work to do this, and you have some lack of information sometimes, and it's there is a database which will be filled now incrementally to fill then new of these steps. And sometimes we say, okay, it's like this step to make it easy, because it's a lot of amount to be done. For the mass production is, of course, this also sometimes not so really relevant, because when you want to calculate your completely impact of your factory, then it's when you have only 2 or 3 process types inside, it doesn't care. Then you can make it really by counting the wafer, and then it's easy. And this is also the case how the most companies made this. But we want to optimize also some process steps. So based on that, we have to also work with a bottom-up approach. But then not for every step, to be honest. When I have only an annealing, then it's easy from that side. But to cover the whole range of etching steps, then we have to structure it in a certain way that we can use the amount of material twice or third.
So what I would like to add, and what Jörg started already to explain, is like, if you use top-down from an economical perspective, that's totally enough. Because the partners say, yeah, okay, we know how much chip area has how much GVP. But if you want to optimize, and like an external vendor comes and says, like, we want to reduce, then you need to find out which process is the most expensive, not from cost, from GWP. And this is only possible with the bottom-up approach, which is expensive, but it's the only way to go for.
Yeah, that's right. And you see it here also for the audience. This bottom-up approach, you have to analyze really each process step and have to calculate everything, and additionally the indirect part. So from that side, this is, but for us, it's very useful when we want to optimize some of the process steps. And when you think about the etching with the SF6, you have here the waste which go outside. It was for a lot of people interesting to see, the impact of the SF6 is much, much higher than everything else we have there working. So that's an interesting fact to analyze and to optimize the process step. But I also want to give you an indication what is the impact of such a complete cleanroom. And I make it easy. I use our 200 millimeter cleanroom. You will see directly afterwards. And as I said, we have about 10 to 20,000 wafers a year. And from that side is 1,500 square meter. And the capacity, as you saw, and we use it for 2020, so it's a little bit some time ago, but nevertheless, the numbers are still valid. And then you get really now some numbers. Electrical power, and this is the most important one. For the infrastructure, we have 5.2 gigawatt hours. That is really large, to be honest. The process equipment, 3.7 gigawatt hours. So in total, we are in the field of 10 gigawatt hours, and this is a lot of. This is in a combination, it relates a little bit how many households you need to think about. But this is about 5 to 10,000 households, only our small clean room here. And this is the most important one, of course. And you see also the infrastructure is much more important based on the circulation of the clean air than other ones. Then we have some heating, cooling, and the other ones, which is also very important, is water. Water, especially from the infrastructure, or what we need for the infrastructure, and so-called deionized water. And this is, of course, something of a very important aspect, especially here in Dresden. More than 60% of the water consumption of the whole Dresden is done here in the north of Dresden by the semiconductor industry. So you see there's a lot of issues. Then we have also the bulk media. That is nitrogen, oxygen, and propane. Propane is not so much, it's mostly for heating. But the nitrogen, this high quality nitrogen, this is also an important aspect. And actually we get it from tanks, from trucks, but we will now also get a so-called Luftzerleger, a separator, which get it directly out of the atmosphere. The atmosphere is nitrogen 80%, and you can really get it out of that, and then you crack it and get it inside our clean room. And to give you then what does it mean regarding carbon footprint, that are 4,700 tons CO2 equivalent per year.
I have a question regarding the
regarding the quantities of, for example, nitrogen, the cubic meters, are they in liquid nitrogen or in standard atmosphere and pressure?
No, gas.
Okay, so standard conditions.
We get it in liquid, and then we have comes to gas. So we get it at liquid at very low temperatures, at the liquid temperatures, and then it will be changed to gas.
Okay, so this is kind of
That's
just for
gas.
calculation at standard conditions.
Yeah, at standard conditions, yes.
Okay,
At standard conditions.
Thank you.
Okay, so we have about, I would say, 5,000 tons CO2 equivalent per year. And when you calculated this with our throughput, then we are in the GVP, so 1.7 kilograms CO2 equivalent per square centimeter. This gives you only a feeling, and I will come to that, what does it mean for the whole industry. But before that, yeah?
How is this with the die area? Is it like a multi-die?
No, only one die.
Okay, only one layer of a die.
Not one layer, really one die. When I stack dies, that's different, but one complete die fabricate.
Okay, thanks.
With all steps. So from that side, when you go to scope 3, it makes much more complicated, because then you have all your supplier you have to take into account. I found this here from McKinsey. They looked into it, and scope 1 and scope 2 takes only 65% of all emissions in the semiconductor industry. So additional 35% are dedicated to scope 3. Of course, it's related where your delivery comes from. So this is, of course, an important aspect. This was for a 300 millimeter fab with 40 to 90 nanometer technology node. This gives an indication, to be honest, up to now, the most of the companies only publish scope 1, scope 2. And scope 3 is still a discussion point. If everybody who can deliver the semiconductor industry can deliver all good values of their products. That's a problem. And how this is now the GFP impact for different technology nodes, and you see here the different technology nodes from 350 to 3 nanometer, and then from some of the calculations over several years, you see the publication, and you see how is the variations over time. And you see a lot of really like a cloud of different volumes or calculations. And it's related a little bit when you have something 2013, and we compare it with 2020, it's a completely different picture. And sometimes it's really the case that also we have for several materials not the right GVP potential out of the database. So that's this really issue, and you see IPMS white there. We are in the mixed field, and for example XFAB you see here, they have also numbers from 2020 on the 350 nanometer node. They are really at the very low end, but you see how the variation is still. But when such numbers is good for us, but to give you an indication what does it mean really for the whole industry, I want to show you one picture, and this is really interesting. You see here on the left side the 2021 Scope 1, Scope 2 exposure of the whole European semiconductor industry. Of course, calculated in a certain way. You saw how much it could vary. But nevertheless, based on that, you see then some different scenarios how it could grow in the future. And when you see 2030 and the pink or the orange part is then Scope 3, that we have really here double or triple the output based on these new installation we are ongoing. And this relates to some additional scenario ideas. The first one is based on ideal, this means 100% renewable energy. And then it could be also 2030 that we are not at 100%. It's also my indication that we have then the European renewable energy target, 42% overall renewable, then it's much higher. And point 3, of course, hopefully it doesn't care, is business as usual, like you have it today or in 2021 regarding the GVP. So, and when you compare it, it means that in worst case, and you see on the right side, that is the of other industry, the chemical industry 2021. And when you compare it, we can overcome the chemical industry in 2030 when we do not sustainable fabrication. When we do it like today and only expand, this will give us into hell, because we are then a really large producer of climate gases. And this is, of course, an important issue, and really also a motivation to do it not in such a case. So we have to reduce, and you see 100% renewable energy is not everything. We have to look also at the materials. And this is our really motivation to work on that into the future in a hard step. In other cases, we get some problems because then the semiconductor industry will be one of the larger exposure or some emittents for climate material. Okay, based on that would be my motivation for the next days. So work on that we get then some possibilities to reduce it and go not in the scenario, especially not the third one, that we can get then also some not too much increase of the climate output or the climate material output, and to reduce it as much as possible. Okay, that's for my lecture. Thanks for your attention, and now you will see hopefully something also in practical way. Thanks.